If you're wearing a pair of jeans, take a look. See if you have that little pocket. That was designed in the 1800s to keep your crystals. All right, this is going to seem kind of like a chemistry lesson, but it has to be said. It's all about the atomic structure. So sticks and balls or balls sticking together to show the internal structure of the crystal. All of the minerals are ordered. They're all going to have this atomic structure. The atoms are going to be different colors in the models, and they're held together by chemical bonds. And the strength of those bonds and the length of those bonds all give us the story of the physical properties of a mineral. Okay, so this example here is sodium and chloride together that makes halite, and it's just a real basic structure, so we use it a lot as an example. The chlorides are the blue balls, and the white ones are sodium. The sodium has that plus next to it. If you've had a chemistry class, you know that that means it's positively charged, and it's attracted to the chloride, which is negatively charged, and therefore they hold together in that ionic bond. The bond type matters. We won't get too bogged down with types of bonds, but just know that it matters. If a bond is really strong, then that mineral is going to be harder. And when we look at hardness of minerals, we're actually talking about the strength of the bond and how easy or hard it is to break that bond. And we test that by scratching the crystal surface, the surface of the mineral. Stronger bond also is going to give the mineral a higher melting point. So then the opposite would be true. So for a weaker bond, it's going to be easier to scratch, easier to break those bonds on the surface of the mineral, and also have a lower melting point. So you can see how that really matters. Bonds also can be different strengths in different directions. I brought with me today a necklace I have of the mineral kyanite. This is kyanite. Let me get it aimed up here. And it has a bond strength that is different along the short axis than the long axis. So it's just a unique physical property of kyanite and other minerals that the strength can be different in different ways because the bond strength, and maybe in the lattice, is different in this direction than it is in this direction. All right, I'm going to turn my face off so we can see the whole screen here. Talking about strength, we're going to use carbon as an example. So graphite and diamond are polymorphs of each other. They both are just made up of carbon atoms, but they have atomic structures that are very different. So looking first at the diamond, the strength of the bonds is very strong between the carbon atoms. Those are covalent bonds. And diamond is the hardest mineral, meaning it's the one that is the hardest and most resistant to scratching. Graphite is very soft. It's what we use in pencil lead. It's also used as a lubricant. It has very slippery surfaces between sheets of carbon atoms. So look at the structure here. In this structure, you have a sheet of carbons that are held together in a fairly strong bond, but then between the sheets are these long orange bonds or weak van der Waals bonds, barely held together, so they have a slippery way that they slide one sheet between another. So they're polymorphs, meaning they have the same composition. They're both carbon, but they have really different atomic structures. All right, here's some different atoms, and these are ions, which are charged particles. Charged particles come about because they've either gained or lost an electron in an atomic bond. So on the left are the anions. These are negatively charged. They're typically bigger. On the right are the cations. They're positively charged. And so a chemical formula is going to be some anion attached to a cation. Notice the anions, because they're so big, they sometimes define the atomic structure, and then the cations kind of pack around those anions. All right, so here's three different um, geometric shapes. So on the left is a cube, in the middle is a tetragonal, kind of a pyramid, and then an octahedral where you've got two pyramids stuck together. And see the difference in the size of the cations there in the middle. Excuse me, the anion in the middle. That's the anion. In the cube, it's bigger. The tetragonal one, it's smaller, and the octahedral maybe a little bit bigger. So you can fit different numbers of cations around those anions depending on the size of that anion. The inside of the crystal then has these atoms. Here's a sulfur and a lead. That's the atomic structure of the mineral galena. Galena is a cube like that. And think of it like this piece of fabric here on the left. The structure repeats. So it never changes from that particular atomic structure. If you do change the atomic structure, then it's going to be a different mineral, like the difference between diamond and graphite. It's always going to be the same on the inside. And if you change the sulfur or the lead to a different atom, it's going to be a different mineral. When we look at, when we think back to classifying minerals, remember a lot of that is done by the shape. So, and one side of that mineral is going to mirror the other side. So here's a look at a halite crystal. It's a cube, NaCl, and the other side of the cube, it's a mirror image of that side. They're always going to be the same. Here's a snowflake also that's showing the mirror image. We also think about minerals as rotating about an axis. So if we put an axis down the middle of a mineral, what will it look like if we rotate it? And rotating it around different axes and different mirror images give us all the different classifications of the geometry of a mineral. When we want to look at the crystal structure on the inside, we use some of these pretty fancy instruments. This one is the XRD. We put the mineral in there and we send an X-ray through it. Here it goes. The X-ray beam goes through the crystal. That crystal and the atomic structure of it scatters that beam and we get a diffraction pattern. So we'll see this as the scatter pattern, and also you can see it as a graph like we saw before. Another way is through the TEM, transmission electron microscope. You can take a beam of electrons, send it through a crystal lattice, and the electrons are going to bounce off atoms. The electrons that make it through the lattice without bouncing are going to make a pattern. So you get this TEM image here with the dark and the light as the beams go through. So these beams have bounced off these atoms and didn't make it, and these made it all the way through. So the dark spots on here are places where there are atoms, and the light spots are the places between the atoms. So it gives you a really profound look at the interior of a crystal.